Hi, Doug here, Bug Amps again, and this is going to be a short, sort of basic discussion about output impedance, Z meaning impedance, and if you're not familiar with impedance is just like resistance, only it's frequency dependent. So if your device, or the thing that you're measuring, changes its resistance depending on the frequency that you're measuring at, then it doesn't have a resistance, it has an impedance. So that's what we're talking about. We're talking about output impedance specifically in regards to power amps in this case, and so we're driving a speaker with these output impedances. And we're going to talk about measuring output impedance and what output impedance sort of means sort of for you and your amplifier's ability to drive a speaker. So let's get started. So you have a device, you've got an amplifier over here, and you've just got, your basic output terminals here, and over here you'll have a load, and the load will be a speaker, but for now we'll just sort of represent it as a resistance, like that. And you're wondering, what's the output impedance of my amplifier? And you're also thinking about it sort of in relationship to the load here. And so the output impedance of an amplifier can be thought of as series resistance with the output of a perfect sort of amplifier, sort of perfect voltage source, I guess is the best way to say it. And so we'll imagine now our perfect voltage source over here, which a perfect voltage source would have an output impedance of 0. And so we'll just put that over here, right? And then we'll imagine the output impedance of our real amplifier as just being a series resistance here. And so this is what we end up having. So this is the ideal amplifier, and then this right here is the actual amplifier there. And so what we're wanting to do is determine the value of this. And as you can start to see now, it's not that hard to do. We've got two values here, and so this can be redrawn as just a simple voltage divider. And we can draw it like this. So we'll have sort of our input here, and then we'll have this right here. That's the, that's not a very good resistor. And then we'll just go like that, right? And so this is going to be the load, and this is going to be the output impedance of the amplifier. So I guess OZ, I don't know. And we're trying to discover what this value is. And so first of all, let's sort of think about what this does. So if you have a voltage here, and this is sort of just V out or something like that, and then you're looking at a voltage here, the voltage is going to be divided at this point by the ratio between these two resistors, and or these two impedances in this case. And so if they were the same value, these two resistors, over here at this point we would get sort of like, V over 2 or whatever, half of V, and then down here obviously is V equals 0, right? And so, so you get full voltage here, and so if your load were exactly the same value as your output impedance, you would measure here, and you would see that you've halved your voltage, right? And so we don't actually have access to this voltage directly, but we can actually find out what that voltage would be, because all we have to do is just unload the output, right? So if we unload the output, then this acts, whatever the output impedance of the amplifier is, acts like sort of infinity load here. So it's like this and then infinity here, right? Because it's not connected to ground. And so if it's a voltage divider between some finite number of amount of resistance and an infinite amount, then all the voltage from the output will be dropped across to the finite resistance right here. And so whatever the voltage is here now is going to be equal to that voltage up there. So this is V out now, I guess. So these guys are going to be equal if you unload the amplifier. And so you take the unloaded voltage output, and so like let's just say for the sake of argument here that we've got our unloaded amplifier here, right? And we've decided that we're just going to set the input of the amplifier so the output of the amplifier is 2 volts, right? So we'll just do 2 here. And when the amplifier is unloaded, now remember there's a series resistance here we're trying to find, right? Like that. And so, but because it's unloaded, there's no voltage drop across that resistance, right? So it's going to be 2 volts here, like that. And so now we know that we have our 2 volts out unloaded. So now what we can do is we can start putting values in here, like this, until we actually reduce this point right here to 1 volt, right? And once we've reached 1 volt there, we know that whatever this value is equal to the output impedance of the amplifier, right? And so we just measure this value then, and we know the output impedance of our amplifier. And so this is theoretic. You wouldn't do this with every amplifier. This is not a good way of measuring the output impedance of every amplifier. But it is a good way of measuring the output impedance of certain amplifiers. And so let me just go over where you would not want to do this. So imagine, for instance, we're measuring a solid-state amplifier, and we want to find the output impedance of the solid-state amplifier. If you just started dropping resistances in here to find out the point at which this value is halved right here to find out the output impedance, because solid-state amplifiers, generally speaking, incorporate a lot of loop negative feedback, they'll adjust the output voltage in accordance with their loop negative feedback to compensate for current draw. What all that means is that they act more like voltage sources, which means they have very, very low output impedances. And so you would actually, before you found the output impedance of a solid-state amplifier, you would reach a value that was dangerous for the amplifier to run at. Okay, so the output impedance of a solid-state amplifier might be something like 0.5 of an ohm or something like that. And it's only rated to drive perhaps 4 ohms, right? And so if you were empirically trying to find the output impedance, then you would break your amplifier before you found it. And so in that case, you need to measure it in a different way. And I'm not going to go into that right now, how you would measure that. But just know that this is sort of a theoretic understanding of output impedance. Although I do actually really like to measure the output impedance of tube amplifiers by actually doing that previous sort of method. And so the reason it works with tube amplifiers is because tube amplifiers, generally speaking, have large output impedance compared to solid-state amplifiers. So, in fact, a lot of people have said, and I think this is true, that a lot of the sound of a tube amplifier is actually sort of it being imperfectly a voltage source. And so, like, the average output impedance of a tube amplifier can range wildly. So, imagine, for instance, that we have just a basic tube amplifier here. So, we've got a tube, right? And here's our output transformer. Right, and this is our B plus right there. Here's our grid. We'll just do like this, right? And it doesn't really matter that much right here, but so now we have a transformer, and usually a transformer is something like 20 to 1 or something like that, right? And so the transformer, like I said, it's going to be like a 20 to 1, something like that. And it transforms the impedance of the plate of your tube by the square of that, right? And so it takes it down quite a lot. So you're like dividing by 400 or something like that. And so if you got, if it's a triode, your output impedance of the triode might be 500 ohms. And so the output impedance of your amp is going to be something like 2 ohms or something like that. That's not an ohm symbol. 2 ohms, like that. And so that's much more than the solid state amplifier's example. Now also you add to this, the 2 ohms right here, it wouldn't actually be 2 ohms if you measure it, because you have to add to that the DCRs of the windings as well. So the DCR of this winding will be small compared to the plate probably. But the DCR of this secondary winding will be large compared to that probably. So you're looking at probably adding another ohm there, you know, something like 3 ohms maybe on something like this. And so, and the other interesting thing about a tube amplifier is because it has a higher output impedance, also the tube amplifiers are sort of the opposite of solid state amplifiers in this other way as well, in that they're basically okay driving a short. Now you don't want to do it all the time or like push maximum power into a shorted output. You're going to cause problems there, but they're perfectly happy to drive low power into a dead short for a short period of time without damaging anything. And so with an amplifier like this, you really can actually just, and this is something that I do, is I'll measure the unloaded output voltage right there, and then I'll just go like this, and I'll take a pot like that, you know, something low value, like I have like a 5 watt, 10 ohm, 500 turn pot or whatever, and you just scroll through or whatever until you reach half the value. So you'd like set this at like 2 volts out or something like that, like I said before, and just scroll this until you get 1 volt here, and then just pull the pot out and measure it, and you will actually get the output impedance of your amplifier. This can be done with preamps as well. Preamps are okay to measure in this way because they'll have an output impedance in probably the 500 ohm range, or up to 1K potentially, or as low as 50. But you can measure the output impedance in that way with a preamp as well, and be pretty safe without damaging it. All right, a couple more things to think about with output impedance is that there's a few things that can change the output impedance of your amplifier. One is you can change the plate impedance of your tube here. And so one way to do that is if you don't have a triode, let's say you've got a pentode, you have another grid in here, right? And so depending on what you do with this grid, it changes the plate impedance dramatically, right? And so if you run it in pentode mode, which is you just take this and connect it to some arbitrary voltage right there, the output impedance of your tube goes from a triode 500 ohms up to probably 10 to 20,000 ohms, right? And so that is transformed over here, and over here, instead of getting like a 3 ohm output impedance, you might get something like a 25 ohm output impedance, something like that. And so that can be a big difference. Also, you could run it in ultralinear, which is like this, where you take like a 40% tap, and that's going to be like split the difference between sort of a triode and a pentode sort of output impedance, something like in the maybe the 1,000 ohm range or something like that, right? And you could also, let's say you're running pentode again, just for the sake of argument, you can also change the output impedance by running loop negative feedback from here back to a previous gain stage, and the more gain you enclose within the loop, the more information you're injecting about the output voltage back to the input, right? And so it knows if the output voltage is dropping, and it adjusts the gain of the circuit. It doesn't just a gain, like it amplifies the difference, right, to try and maintain a voltage. So it makes it act more like a voltage source. And so that will also change the output impedance of the circuit. All right, now that said, why? Why do we care? Why do we care about output impedance? And so there are a couple things that are important to think about with output impedance. And so one of them is dampening, and the other one is frequency response. So first of all, let's talk about frequency response. Now, remember, we have our voltage divider here, and this is the output impedance right here, and this is the load. So the load in this case is a speaker, and speakers don't have a fixed resistance, right? They don't have that, so what they have is an impedance curve. And so here we look at like sort of a typical impedance curve for a woofer. And so over here we have impedance in this direction. So that's Z, and down here we've got frequency, right? And so you can see that depending on the frequency that we're amplifying, we're going to have very different impedances in the second part of that voltage divider. And so we're also going to have very different, so here's our voltage divider again. Here's our amp, here's the output impedance, here's the speaker, and we're looking at this voltage right here. And so depending on what frequency we're amplifying, this voltage here is going to vary a lot if this value is large, right? So if this value is large, the voltage here is going to vary quite a lot, right? So now you're understanding maybe why they call low impedance sources voltage sources, because if you make this value very small, it doesn't really matter what the load does, this voltage changes very little. And so this is important because when people are designing a loudspeaker, they're kind of assuming a voltage source. And so they're going to be looking for arriving at a frequency response that's flat, like this. We're going to put the frequency response up there. We want a flat frequency response for our speaker, right? But this is only generally the case with a very low output impedance amplifier. And so if you have a high output impedance amplifier, when the impedance is low, you get a little bit of a dip in frequency response. And when the impedance is high, you get a bump. So you might have a new frequency response for your speaker that looks kind of like this. And so that will be exaggerated more or less by the output impedance of your amplifier. And so this might be some of the reason why some speakers sound better with tube amps than solid state amps. And that's because if this is a woofer, for instance, resonance a lot of time is down in like the 35, 40, 45, 50 hertz range. And that's actually a pleasant range for a little bit of bump in the low frequencies. And it might be a couple few dB or something like that. And then also you'll notice as the speaker becomes inductive up here, we get a little bit of a rise. And so let's say, for instance, this is a woofer, but let's just say this is a high frequency driver, something like that has a little bit of an inductive impedance rise at the high frequencies. Well, look, you get a little bit of a boost at your high frequencies. And so you can see this is actually a little bit of a kind of pleasing. You've got a little bit of a dip here in the mid-range, you've got a little bit of high-range sparkle, you've got a little bit more in the bass frequencies. And so I think a lot of what people hear, when the initial thing that people hear when they switch between perhaps a tube amp and a solid state amp, is just the slight frequency, we're talking about a few dB in here, a slight frequency response difference depending on the speaker. So that is one thing to consider. Next thing to consider is dampening. So dampening is interesting. And I've got an example here. I actually have a physical couple speakers here. And I'm going to show you the difference in dampening here. Make sure I'm still recording. Yes, I am. All right, so I have this speaker. You can kind of see it. It's just like a PA speaker kind of thing. Came out of an old bass cabinet. And I'm going to put it over here next to the microphone and just go ahead and listen to this. Can you hear the resonant frequency? That's the frequency that the speaker naturally resonates at. Now what I'm going to do is I'm going to short the speaker out, the speaker input there. So what that is simulating a 0 ohm output impedance for an amplifier. You hear that? The resonance is completely gone. Alright, so we got that one. I have another one here. Just so we can see, it's not just that speaker. Mostly this is woofers, but... Alright, so here we got a nice old Electro Voice woofer. It's actually got a whizzer on there, so it's trying to be full range, 15-inch woofer. Alright, listen to this. You hear that? We'll short the input there. So it's that versus this. All right, and so what's going on there? What happens is that a woofer, it's got mechanical dampening. So here's like a woofer, right? I'll just go like this. This is the side view, right? So we got our former down here, our voice coil. Here's our magnet gap, right? Like right here. Here's our magnet. And here's our plate down here, and there's obviously like this in between there, and the coil doesn't go all the way to the bottom, of course. And so what's happening here is that the woofer has lots of different ways of sort of dissipating the energy. So you're putting a tone into it, but when you're done putting the tone into it, ideally you want the speaker to stop making sound, and so it does this in lots of different ways. It'll just radiate it away into the air, obviously, as sound, but that's undesirable because you don't want sound coming out that you didn't put in necessarily. And so you've got mechanical dampening. So these right here, the surrounds, mechanical dampening right there. You also have a spider here, like that. This is mechanical dampening. And whatever the cone is made out of will be designed to vibrate at the frequencies it's supposed to be operating at, but it will probably be designed to not vibrate at the frequencies it's not supposed to vibrate at, and so it's dampened slightly there. It's also going to probably be, let's say, in a cabinet, and the pressure of the air in the cabinet will also dampen the woofer somewhat. And so it's all those things are dampening, but there's another kind of dampening, and that dampening, as you might expect, is actually the output impedance of your amplifier. And so if the output impedance of your amplifier is high, you're going to have more what's called ringing. The speaker will tend to move at a frequency that it naturally vibrates at after you're done providing it with acoustic energy, and it will ring. And so that is, and so if you have a low output impedance, it actually soaks up that energy via the magnet coil motor structure. So I don't know if you're aware of this, but if you push on a speaker, you generate electricity this way. And that's sort of back electromotive force, I think is what they call that. And if your output impedance is sufficiently low, like let's say it's something approaching a dead short, it just dissipates that right there at the amplifier, and the woofer does not resonate at all, just like we sort of showed when we shorted the outputs of those woofers, right? So if your output impedance is higher, you can have a little bit more ringing. Now, this is interesting because subjectively speaking, a little bit of ringing doesn't actually sound bad. It can sound muddy to some people, but it can also sound kind of full. And it really depends on the speaker in question and what frequency it likes to resonate at in the enclosure that it's in. And so this is another reason why some people might find a certain speaker to be tube friendly. And so having a slightly higher output impedance, or a slightly lower dampening factor, as it's called in the literature or in a spec sheet for a solid state amp, having a less dampened system can actually sound nice. So we're talking about having no dampening. Obviously, it's still going to be low-ish. We're talking about 5 ohms versus 1 ohm or something like that. But it can change the distortion also of the speakers. Obviously, getting tones out of your woofer that are not the tone that you put in is distortion. But I think that's basically what we're talking about. Tube amps, we're talking about a little bit of distortion that is pleasant. And so we're getting, like I said, so the output impedance will change your frequency response a little bit. It'll also change the dampening characteristics of your drivers, particularly your woofers, in the bass frequency range usually. And so that's sort of like the briefest sort of overview of output impedance and why you should care. All right, hope that helps.